So this is a contraction of a lecture course I gave in Halle. So the original thing was about 10 hours. This is going to be less than that. You'll be pleased to know. You're going to get lunch. So the title does seem very vague, but I'm going to try to justify the vagueness of my title. So I'm going to start a bit by talking about, so I want to give a feeling for like what are hard problems in group theory. And in particular, I am, to be clear, not suggest like some problems are, it has taken many people a very long time to figure out how to do them, but then once we figured out how to do them, they're easy. But some things are easy, so like if you have so everything I'm going to talk about, I'm going to be talking about finite permutation groups. So things like the orbit of a point, the stabilizer of a point in a permutation group, finding a minimal block system, we can do all these things quite quickly. Some things are easy for some groups. So yesterday, Muncie talked about finding normaliser for, I should have said, I apologize, I haven't got the full thing, for highly intransitive non-abelian, subdirect products of highly intransitive non-abelian simple groups in the symmetric group. She was too polite to say this, so I will. Muncie is mine and Colbert's PhD student. She's excellent. She will be finishing shortly. We don't have money to keep her on, which I am sad about. If you are looking for the type of postdoc who can reasonably understand what she was talking about and this type of stuff as well, then, yeah, she might not want to work on this, but she does understand it. Then there's a bunch of problems which are generally thought to be hard. So things like finding the normalizer of a group in another group, intersection, centralizer in a group, set stabilizer, so a subset of omega, a partition of omega. And so there is some results known for these. So it's known that intersection, centralizer, and set stabilizer are all easier than normalizer. And also all these problems have what are often called the transport or the coset variant. So I can ask for the intersection of cosets. I can ask for an element which conjugates one group to another, either in the symmetric group or in a given group. I can ask for an element which maps a set to another set within a group. So once again, some of these. So this problem is always hard, even if I don't give you G. If I ask you for a permutation which maps a subset of omega to another subset of omega, that is not a difficult problem. But it becomes difficult when I tell you you are restricted to a given group. Now, I am not going to talk about here, there's been recent work, so Babai has done work on graph isomorphism, proving it's quasi-polynomial. That work has been extended to some of these classes. As of yet, none of those algorithms are of practical value, and Babai has said himself that he doesn't think that it's of practical value. That doesn't mean that there isn't a clever person who can figure out how to make it into a practical algorithm, but as of yet, we don't have one. The main paper, if you do stuff in GAP, you are using this paper by Jeffrey Leon. So Jeffrey Leon unfortunately passed fairly recently. So I am in this talk going to be mean to this paper. This paper is, the reason I am going to be mean to it, it is an incredibly important paper. It is, in my opinion, by far the most important paper, which basically nobody understands. So I came to this paper, so Steve Linton had been trying to work on this paper with some people at St Andrews, not getting very far, and he found 6 months' money down the back of the sofa and basically gave me a postdoc for 6 months where my only job was to read and understand this paper. I failed, but I got so involved in it, I carried on working on it. I then got the Royal Society to give me 5 years' worth of money to fully understand this paper and re-implement it all. I failed. I then got the Royal Society to give me a 3-year extension, and now I have succeeded. So, but the abstract is good. So, the abstract tells us, I'm going to read the abstract out. A technique for computing in permutation groups of high degree. The technique uses successive refinement of ordered partitions introduced by Brendan McKay in connection with the graph isomorphism problem to supplement the techniques of Basin-strong generating set developed earlier by Sims. And that's basically what he did. He took this work of Sims, combined it with the work of McKay, and made the thing which basically both GAP and Magma used to do all the problems I discussed earlier. So I'm going to give a very brief overview of the work of Sims and the work of McKay, and then describe how we combine them. I am not going to have time to go into all the details. My plan is to give you the big picture. If you're then interested, you're then in a position to learn more about this. Feel free to email me. I have read this paper, so you don't have to. So just to say, so there are no known practical sub-exponential time algorithms for solving these problems. Now, the most obvious way of finding an element of a coset would be we could make every element of one of them and check if it's in the other one. We could do that. Nothing I'm going to describe beats that. There is nothing known that beats that, which is also practical. And it is not hard to hit this worst case. So we have examples in both GAP and Magma where we can make GAP and Magma do this. So it's not even that this is a theoretical worst case. We can hit it on purpose. Now, if you don't know about base and strong generating sets, I don't have the time to explain it, I would strongly recommend going away and learning about them. Base and strong generating sets, Schreier vectors, if you haven't come across them. They're fundamental to basically everything to do in group theory. For the purposes of this talk, they have two important purposes. If I have a group given as generators, I can efficiently find, given two lists, x1 to xn, y1 to yn, is there an element of the group that maps each of the xi's to the yi pointwise? It must be pointwise. Going back to earlier, if you ask, can I map this as a set to this as a set, then no, we're back to something that's super hard again. And I can also say, what is the stabilizer of a list of points in G? So I can do point stabilizer. Once again, can't do set stabilizer. So as far as I'm concerned, these are the two things that base and strong generating set provide me. So let's imagine that we were trying to intersect two groups. So we'll start by picking some point, which is, and its orbit in G isn't just the identity, and its orbit in H isn't just the identity. If one of G or H fixes every point, their intersection is the identity, and we're done. Then, based on the type of thing Richard Parker did, go and find the intersection of their point stabilizers. How you do that is, I mean, this is a recursive call, so we'll do what I'm about to do now. After we have found that point intersection, all we need to do now is find all the cosets of that subgroup. And once we've got a subgroup and we've got all its cosets, we have our original group. We know what the cosets will look like of the point stabilizer of alpha, is they'll map alpha to different points in each coset will be represented by where it maps alpha to. We know that the orbit of alpha in the intersection of G and H is going to be contained in the intersection of its orbits in G and H. It might well be smaller, but it will be that. So then basically for each of these elements, we look for some element in the intersection such that alpha to the G equals beta or proves non-exists. So now I'm going to talk about how we do this bottom bit. And basically, there's not a good way of doing this. So I'm going to start by trying to solve a more complicated problem, then go back, which is I'm going to ask, how can I solve the problem? Is there a G in G intersect H which maps a list of points to a list of points? Now, you will remember from earlier, if I give you a group, then base and strong generating set will solve this problem. So your first instinct might be, you already know how to do this. You can ask if there's such an element in G, you can ask if such an element in H. And of course we can, but the element we find in G might not be in H, the element we find in H might not be in G. So, and there is not a way of saying, give me one which is in both G and H. When we go and look for one, so base and strong generating set can tell us if one exists. So the way we're going to do this is we pick some alpha n plus 1 we haven't fixed yet, and alpha n plus 1, well, I mean, it has to go somewhere. So we can try every possible place it could map to in omega, so the values which are not in here, and say, is there an element of G that maps this to this? Is there an element of H that maps this to this? If there isn't an element of G, if we ask G, do you have an element that maps this to this, and it says no, well, there obviously isn't one in the intersection. If we ask H as one, and it says no, there obviously isn't one in the intersection. If they both say yes, we can check. If they both say yes and they happen to give us the same permutation, awesome, we've found the thing in the intersection. If they both say yes, but they don't agree on what it is, we fix another point, we keep going down. Eventually, we'll either find something, or we'll work our way through the whole coset and find nothing. And indeed, that case where you work your way through the whole coset and find nothing doesn't happen infrequently, which is quite annoying. So, like, what have we gained? So before I said just enumerate the whole coset, we've gained two things. This idea of early search termination. Instead of trying whole permutations in H and seeing if they're in G, we say, well, is there something in H that maps 1 to 2, 2 to 3? If there is one of those in H, but there isn't one in G, there's no point checking every extension. And also, coset representatives. In each coset, we only had to find one thing. Once we found one thing in the coset, we're done. The following I leave as a sort of example to the reader. Once you find something in one of the cosets, that might also find you other cosets. So if that coset map 1 to 2 to 3 to 4, then you've actually found a whole bunch of cosets. And once again, if you read papers on this topic, you can find good details on how to do this. Very good source for material on this is Suresh's book, and Alexander Hupka has a set of group theory notes. If you Google for Alexander Hupka group theory notes, they'll turn up on the internet. So that's a very, very quick overview of Sims work. So now I'm going to talk about graph isomorphism. And so here's a graph. So McKay originally published this in 1978. He did a paper called Practical Graph Isomorphism. A few years ago, he wrote a paper called Practical Graph Isomorphism 2, which is basically just has some new stuff, but has much more examples. It's now in color. All the pictures are nice. So if you want to understand this, this is the paper to read. And so the fundamental observation for graph isomorphism is, so we have this graph, and we want to find automorphisms of this graph. So vertices, the idea is this vertex up here has 3 neighbors. This has 3 neighbors, this has 3 neighbors, this has 3 neighbors. The vertices which have 3 neighbors must map to vertices with 3 neighbors. And these vertices have 4 neighbors, and these two have 2 neighbors. So in the same way as before, we could find the automorphisms of the graph by just trying every way of mapping the vertices to the vertices. But instead, we map things with the same number of neighbors to things with the same numbers of neighbors. Except we can do better. So if we look at this vertex up here, now we've colored the vertices. I apologize if I have any colorblind members of the audience. This vertex has 3 purple neighbors. This vertex has a purple neighbor, a blue neighbor, and a blue neighbor. So this vertex can't map to this vertex. So I can run my coloring again, now looking at the colors of my neighbors, and now I discover that these 2 vertices might swap, these 2 might swap, these 2 might swap, these 3, and then this one is fixed and this one is fixed, and I can run it again, and now it reaches a fixed point. So I can run my algorithm a few times till it reaches a fixed point. Eventually I get stuck. So what I'm going to do now is I am going to fix this point up here. So I'm looking for automorphisms of the graph which fix this point. I've made it a new color which nothing else has. And then I run the coloring algorithm, and I run it, and so you can see now this has changed to a color nothing else has, this has changed to a color nothing else has, this has changed to a color nothing else has, and now everything has a different color. I promise there's a limited number of colors you can use. What we have proved, purely sort of using combinatorics and a bit of numbers, the automorphism group of this graph, when you fix this vertex, is trivial. So great. And we also knew the only place this vertex could map is here. So we're well on our way to figuring out. So there's now only one. We know the group is at most size 2, and the only question is there something that maps that vertex to that vertex? And if so, what is it? What we do now is we duplicate the graph. And in this one, we color this one brown, and this one we color this one brown. Now, it's really obvious but really important. If I run the coloring algorithm now, so at the moment, things in this graph can map to things in this graph. When I run the coloring algorithm, so now there's one thing over here that's green and one thing over here that's green. That means if there is an isomorphism which maps this graph to this graph, there might not be one, but if there is one, it must map that vertex to that vertex. And I can carry on running the coloring algorithm, and every vertex ends up with a unique color. I have not proved, just by the coloring algorithm, that there is an automorphism that maps the first graph to the second graph. You have to. We now know there's only one possible mapping, and it's a mapping that maps that to that, and the green to the green, and that one to that one. You still have to build the graph, apply the permutation check. This does not claim to solve the problem of graph isomorphism. It just greatly speeds it up. Now, sometimes you might have a graph that's harder. So here's a graph. It's a regular graph. It's the front graph for those who recognize it. And this graph, all the vertices have degree 3. So we run our algorithm, it doesn't do anything. It's sad. But we can still do our coset. So let's figure out if there's a permutation that maps that vertex to that vertex. So we look at our neighbors, and well, this tells us that those 3 blue neighbors must map to these 3 blue, and all the yellows must map to all the yellows. And I can run it again, and this tells us like the reds map to the reds, and the green map to the green, and the yellows map to the yellows. And the eagle-eyed among you will have spotted a problem. There's several problems. There is 4 yellows here, there is 3 yellows here, these aren't going over here. What this demonstrates is that there is not an automorphism of this graph which maps this vertex to this vertex. This is in fact computationally the more important part. So most people, I think, feel like the important thing about the refinement operation that Mackay does is the generation of orbits. In practice, it's not. The important bit is detecting that there is no automorphisms between 2 graphs. This is what we really care about in practice. If you delete the bit where you do the orbit distinguishing and just do this, it slows down, I mean, maybe a couple of 100 times. If you delete this bit and just use the orbit splitting, it takes years for things that used to take seconds. So I now want to try to formalize what we just did. What we did is we had a function from our set omega to some colors, and what the contents of this set are immaterial, they're just identifiers. We can act on that set by, if we apply symmetries, if we apply permutations in omega, they map the base set, and when we have 2 of these functions, we say we want the things which map the first function to the second function. This is a group when these 2 are the same, otherwise it's a coset. So going back, just to sort of, so we're saying here we have a function that maps vertices to color, here we have a function that maps vertices to color, and then we have the set of things that map this to this. There is a good chance, because I keep doing this, that I'm going to keep using the word coset. Whenever I say coset, assume, like, you keep having this case. It's either a coset or it's empty. Now, the empty set isn't a coset, but actually, it's just, in this case, it's irritating. So whenever I use coset, put the word empty if I forget. So what do these functions have to do? So the important thing back here, so there were 2 things this did. It gave us a better approximation of the automorphism group. When we just had 1 graph, and when we had 2, it gave us a better approximation of the mappings from here to here. So if we claim we have a refiner, so refiners always come as a pair of functions, and they take one of these mappings to colors, and they produce a new mapping to colors. So if this is the group or coset we're looking for, what this is saying is, if you find all of the things that map your first thing to your second thing, which are in your group, after you run your refiner, it has to have all these things in. These were the permutations we were looking for, so we better still have all those permutations. The reason for this subset is because, I'm going to come back to this in a minute, the reason for this subset is we assume these things provide new information. They don't have to retell you things you already knew. So in particular, a valid refiner is the identity function that just whatever you gives it just says, everything's 0, no, don't have any opinions. Is a perfectly valid thing to do. It wouldn't be useful, but you could do it. And then when we put this in a computer program, we take our current state, we run this refiner, we basically replace our current state with the sort of pair which consists of the old information we knew and the new information we just learned, and hopefully this distinguishes some more elements of omega than we knew before. In particular, obviously, if 2 things were distinguished after I run the refiner, they're still distinguished, because I keep the information I had before, I just keep gaining new information. A very brief sidetrack for anyone who has tried to read Leon's paper. He does not do this, he has ordered partitions. An ordered partition is basically the same thing, where you throw the colors away and you just have numbers. Computationally, if you remember the colors, actually you get better performance, but otherwise an ordered partition is just a set of numbers. He also has a whole set of weird and wonderful extra conditions these things have to implement. These are all just to do with his implementation. There's no mathematical requirement for them. They do make it faster, and the way everyone uses it, but they're not mathematically relevant. They're just there to make the implementation go faster. So the idea is, if we want to actually use this in search, we're going to do a sim-style search as before, so we're going to search through all the permutations. We're going to keep fixing points. But now when we're trying to find an approximation for the orbit of alpha in G and H, we're going to let our refiners give us their opinion on what the orbit might be. And also, if at any point we notice this thing where we have like 3 yellows and 4 yellows, then we'll go, nope, there's nothing here, stop and backtrack. So I'm going to go through an example. I'm happy to tell people afterwards if they can't guess right. So I'm going to intersect 2 groups. I am intersecting, like, there are some real groups here. I aren't going to make up fake orbits, but I don't want to tell you the groups because I only want you to see what the algorithm would see, because otherwise you would just trivially, I'm sure many of you could tell me in like 3 seconds what the intersection was, and I want you to have to use only the information that the algorithm is allowed to use. So I'm going to start, and I start by saying, what are the orbits of my 2 groups? They're both transitive. A refiner says, yeah, like, I don't know anything. I still don't know anything. There's nothing to do. If you try to intersect transitive groups, there's literally no progress you can make. I mean, because the group is transitive, the refiners are not allowed to distinguish points because that would mean that the intersection was non-transitive. So I will take a point and I will fix it. Because C can contain, as I said, the labels are immaterial, I'm going to label the first thing with a branch and then just leave 0 for everything else. And then I'm going to say to the refiners, right, if I say that the first thing is branch and everything else can permute around, what do you do? And this is equivalent to taking the point stabilizer and taking the orbit. You'll remember from earlier, point stabilizers can be calculated cheaply using a basic-strong generating set. So I ask G what its orbits are, I ask H what its orbits are, and now I might go on just to check if people are awake now, they've had enough coffee. Can anyone tell me some fact about the intersection of G1 and H1? Given just the information from the orbits, there's actually quite a bit. That is true. We can do quite a lot better than that, though. God, so I'll pick through a few. So actually, it's easier, I think, if I write down what the refiner's going to return. What the refiner's going to return is, so these are like the numbers in order. So it says 1 is in the first orbit of G and the first orbit of H. 2 is in the second orbit and the second orbit. 3 is in the second orbit and the third orbit. 4 is in the first orbit and the fourth orbit, etc. This is in the first orbit and the first orbit. 2 is in the second orbit and the second orbit. These two things are different, therefore you can't map 1 to 2. And in fact, the only two things in this list which are identical are 5 and 9. So just from this orbit information, I know that G1 intersects H1 fixes 1, 2, 3, 6, 4, 7, and 8. So once again, we're most of the way there. And if we'd done sims, we wouldn't have known this. We would have had to start going, well, where's 2's going, where's 3 going, where's 4 going. So almost immediately, the entire problem has collapsed. And so this is a common thing for any example where you're doing. This isn't a theory, but in practice, if you use Leon's stuff, if your group is a low-order transitivity, there's a very good chance it will solve things extremely quickly. Because as soon as you start getting orbits, things start happening. So now I'll fix 1 and also 2, and I'll run this function again. So here's the things for 1, here's the things for 2, and I can sit and read off so we can see 1 has to map to 2, and 2 has to map to 1, 3 has to map to 3, and you can work your way through and figure out where all the things map to. And we do still have a choice. 5, 9 has to map to 4, 9 in some order, and we don't know. So, and I'm not going to go through this, we would fix 5, and we'd say, right, 5 either maps to 4 or 5 maps to 9, and we have a little tree, but it doesn't take very long. Once we solve this, we will get a permutation. That permutation will tell us 1 and 2 swap around. Unfortunately, that doesn't solve any of the other cosets, which is a shame. But we can carry on, and eventually, we will at some point try 9, and we'll do this thing again, and we'll make the functions for G, and we'll make the functions for H, and this time we'll start going things like, what is this nonsense? Like 4, 3, 4, 3, 4, 3, 4, 3. Like there's only 1, 4, 3 up, 2, 4, 3s up here. There's 4 down here. There ain't no element of this group which maps 1 to 9 of the intersection. And we can just read this off from this information. We don't need to do any clever group theory. So we immediately know that there is not an element of the group that maps this to this. So just to kind of go over this point again. So a way of viewing what we're doing, if we have a refiner for a group C and a refiner for a group D, their composition is a refiner for C intersect D. And this is a fairly easy proof from if the first refiner preserves C and the second refiner preserves D, they both preserve C intersect D. And so if at any point we realize, after applying some refiner for C, refiner for D, we can tell that there are no permutations that map the first to the second, then we know that wherever we started from doesn't have any elements of C intersect D. And once again, it's this violation, it's this detecting violation which is the important part. The orbit approximation is good, but actually if you turn it off, almost immediately the search would realize it was going to backtrack anyway because of this. In fact, you can prove that the search only gets one level deeper. You can prove if you would have done an orbit approximation, the next level would have detected it anyway. And broadly speaking, this is what Leon did. There's a whole bunch of things I'm not going to tell you about, which is how you make it go very quickly. So kind of related to what was discussed earlier in the week in matrix groups, in the metax and things, I would say, like, so in the ethos when you're doing this kind of search is you end up doing a lot of very simple things, and a lot of the things you do are very similar. So we take a group, and then we fix a point. And later on, we just take the same group, but a coset of it, and then another coset of it. You must do as little work as you have to do that you already did. You end up remembering huge amounts of things you did, so you don't have to do them again. So I have two implementations of this code. Both are freely available and integrated in GAP. One is called Ferret, and it's a C++ monstrosity, but it's very fast. It's comparable with Leon's code. The other one is called Backtrack Kit, and it is supposed to hopefully be easy to understand. They both produce the same size searches. They both do the same things, and the main difference is Backtrack Kit, every node of search pretends it's starting afresh. It doesn't remember anything it's done before. The search sizes are identical. Backtrack Kit's like 10,000 times slower. So we're not talking like 10 or 5 times slower. It is a huge amount of work. If nothing else, this also, if you run Leon's code, while we know that calculating base and strong generating sets is very quick, in GAP, this algorithm often spends something like 99.5% of its time calculating base and strong generating sets. So while it is a thing which is fast, everything else is even faster. And you need a whole bunch of base and strong generating sets, and that does slow it down. So I'm now going to give some concrete examples of these refiners. So just to sort of go over what we were saying before, what we do for a group. So if I have a group and I get given the current state, I take the points which are fixed. So the points which are fixed are the points where there's only one thing with that color. I fix those points, and then I calculate the orbits. There's one bit, once again, I want to be honest about the bits I'm not telling you. You will have noticed I ordered the orbits. I called them like 1, 2, 3, 4. It is not the orbits must be consistent in a certain way, which is boring and technical to explain. So you want that when you fix 1 and when you fix 9, in some sense orbit 1 is the same orbit, and orbit 2 is the same orbit. It's not difficult to do, it's boring and technical, and you can do it. And if anyone wants to know the details, I'm happy to tell them. We can write a refiner for set transporter. So this is mapping a set to a set. So the refinement for set transporter just says, we have these two functions. The first function just says, I'm going to say that everything which is in the set A, I'm going to mark as true, and everything which is not, I'm going to mark as false. And the second one says, everything which is in the set I'm going to mark as true, and everything which is not, I'm going to mark as false. And you can convince yourself that the things that map this function to this function are indeed the permutations which map the set A to the set B. One of the reasons I wanted to give this is to give you a feeling. This by itself is stupid. I mean, we don't need this to tell us how to map sets to sets. Also, it feels like it doesn't do anything. I mean, it's just two constant functions. But when you put it in the code at the same time as this one, now you have set stabilizer, and set stabilizer is an interesting problem. And genuinely, when you ask GAP to do a set stabilizer, it takes this function, it takes this function, and it runs them both at the same time. So there's no magic. It doesn't have any special concept of set stabilizer. It just does. It's in the group. It stabilizes the set. That's all we do. So there isn't kind of magic hiding behind the scenes where it knows something clever about set stabilizers. And of course, you can keep combining these. So if you wanted to say, and people have wanted to do this, I want to stabilize sort of this partition and this partition and this group and this group and also the automorphism group of this graph, you can pile them all in at the same time. And generally speaking, the more of these you pile in, it only tends to get faster as a rule. The group gets smaller. It's definitely never worth doing some of the intersections and then some more. You should just pile all the functions in at the same time. So normaliser, there is a huge body of work on writing normaliser refinement, so I'm not going to do all of the work on normaliser. Normaliser is the one place where people have done interesting work on writing clever refiners. If anyone wants to take something away from this, one of the things I think is these refiners, once you understand how things work, you just kind of write your own refiner for your thing and plug it in. You shouldn't have to understand the rest. I work on as well as doing this, I also work in AI, and I work on an AI logic system, which has a very similar flavor to this, and it has what we call refiners here, I call propagators in AI. It has like 60 propagators, which were written by like 15 different people. Sometimes PhD students send us a new propagator. They don't understand how the inside of our AI system works. I don't understand how their propagator works, but it's all fine. We pile them all in, we solve our problems, everyone's happy. And you shouldn't have to understand everything to be able to write one of these functions. But you kind of do at the moment, but hopefully we'll get to the point where you don't have to. But just to say, a way of doing normaliser is, as I think everyone knows, normalisers preserve the size of orbits. So a thing in an orbit of size 3 has to map to a thing of orbit of size 3. So if we just map every point to the size of the orbit that it's in, that will be preserved by the normaliser. This is a very respectable method of finding normalizers, it turns out. It might look very stupid, but remember, once we start going down the levels of search, we'll start getting more orbits. This will interact with other refiners. And as I sort of said earlier, if you want to find the normalizer of a group in another group, when you're in the backtrack part, GAP does the normalizer in the symmetric group intersected with the original group. There is, and I'm sure some people here could talk about this, there's a little bit I'm hiding here. Actually, when you ask GAP to do the normalizer, it will often try to do intelligent, clever things before it hits Leon's code. So often it will figure out that it can rewrite the problem to a problem on a smaller set of points. Once it hits Leon's code, then it just starts doing this. Then it doesn't do anything clever. But there is things you can do before you hit Leon's code. Once again, I don't want to get into all of those. So what are the limitations? Why are we not just done? Like, on the other hand, Leon did this code, and basically everyone's used it unchanged. And, I mean, most people seem relatively happy with it. But there are problems that it has. And in particular, it doesn't do well with transitive groups. So as we said, when we're taking a group and we're trying to intersect it, what I said was we take the points which are known to be fixed, and we take the orbits of those fixed points. Often our state might know, like, oh, like, here's 5 things that map together, and here's 5 things that map together, and here's another 6 things that map together. That information is just ignored by the refiner for in a group. It just says, I care about the fixed points, nothing else. Now, the obvious thing to say would be, oh, well, why don't you just take the group and calculate the stabilizer under the sets, except that's set stabilizer, and this is how we solve set stabilizer. So we can't just say, oh, like, we'll just do set stabilizers. That's not possible. Sometimes if the sets are very small, like size 2, you can kind of kick it till you get a set stabilizer out, and it is sometimes worth the effort. But it doesn't feel like a great idea. So far, we've only been looking at orbits. We've been taking groups, looking at their orbit structure and nothing else. What other information can we use? Now, remember that the game we're playing here, we know that the thing we're solving is exponential time, and we're not expecting a theoretical gain in performance. So anything else we do has to be worth the search reduction it does. So there's lots of properties we could figure out, but it would take longer to figure them out than it would just take to find whatever we're trying to do, the intersection, the normalizer. So we can't just start reaching into a sort of group theory book and pull out all the things. There are lots of things we can do, but we can only do things which are cheap. A good candidate is orbital graphs. So for those who haven't heard of them, it's very simple. If you take a group, it's literally just so an orbit is just the orbit of one point. An orbital graph is the orbit of an ordered pair of points. So you just have a graph. The vertices are omega, and the edges are the images of this ordered pair of points under the group. Now, it's not super complicated. The automorphism group of this graph contains G, because obviously, if I take any edge of this graph and I apply an element of G to it, I get another element of this, another edge of this graph. That's how I defined it. The automorphism group may well be bigger than G, but it certainly contains G. And they can be found and generated very quickly, and they're well studied. They could be better studied. There's still stuff to know about them, but they are well studied. We know quite a bit about them, and we can knock them out quite quickly. And on a practical perspective, once we start having graphs, our immediate thought is, aha, we get to go back and ask Brendan Mackay how to do it. And broadly speaking, and I'm happy for someone to tell me I'm wrong, like naughty is never the limiting factor in any practical program. I'm sure I'm going to have people tell me wrong. In particular, in our latest code, often when we solve problems, at every node of search we run naughty. So we've technically turned an exponential algorithm into a doubly exponential algorithm by every node running another exponential algorithm, and yet it's still much faster. Naughty can calculate usually the automorphisms, so I can take a group, I can ask naughty to find the automorphism groups of all of the orbital graphs. I can ask GAP to find one Basin-Strong generating set, and naughty will have found all the automorphism groups of all the orbital graphs, which is supposed to be exponential time, before GAP has built one Basin-Strong generating set. And this is not GAP like Basin-Strong generating set is one of those algorithms which is polynomial but irritatingly slow. I mean, it's low-order polynomial, but it's still annoying. I've actually kind of put these in the wrong order. So Heiko Tyson wrote a thesis which I'm not going to attempt to pronounce the name of. But the important bits are, so I'm going to say like methods for normalizers in permutation groups. This is the important bit. He did other stuff as well. And he pointed out that the automorphism group of the set of orbital graphs is preserved by the normalizer. And so he wrote a refiner where he would basically take the set of orbital graphs, do a little bit of pre-processing, and then just say anything which preserves this set also preserves the underlying thing. And you can do, with a bit of sort of work, you can do something very much like the coloring we did at the start with a set of graphs. What you can't do is color each graph one at a time, because you have to treat them as a set. So you have to make deductions like, well, of these graphs, if this vertex has 3 neighbors in 3 of them, and this vertex has 3 neighbors in 2 of them, then this one can't map to this one. And you do that reasoning, and it works quite well. This is one of those papers which is super weird. So we wrote, so this thesis is quite old now. I'm going to admit myself, Marcus Fry from Rebecca Waldecker wrote a paper where basically we said the automorphism group of the orbital graphs individually contains G. And this is one of those weird papers. On one hand, this is obviously simpler and basically an extension of this. On the other hand, no one had done that for 20 years, and it sped up loads of things by thousands of times. So, I mean, it kind of felt almost bad writing the paper. It felt like we're just taking this work and making it even simpler by removing the set. But when you add it, it makes things much better. We did do a bunch of, once again, there's a bunch of stuff in that paper to do with making it go fast. You don't want to build all these, keep rebuilding all these graphs and running the refinement all the time. Just to give you a feeling for how this works, so here's an orbital graph. And if I wanted to calculate the set stabilizer of the set 1, 3, so normally if I was running partition backtrack with the normal refiners, I'd end up with a partition where 1, 3 was yellow and 2, 4, 5, 6, and 7 were white. I would take the refiner for the group. The refiner for the group would say, is there any fixed points? No, and it would do nothing, and we'd have to start branching. Whereas now we have this graph, we can run naughty, and naughty says, oh, well, I can deduce like these 3 points are fixed, because 2 is the only thing that has a yellow coming in and out, and this is the only thing that has a yellow going in, and that's the only thing, and then rapidly you fix all the points. So this can detect that this can detect almost immediately that the graph is fixed. And yeah, so it goes through and it fixes all the points. This is obviously a very simple example. I mean, yes, if we wanted to calculate set stabilizers and cyclic groups, if this was the cyclic group, then this wouldn't really be worth doing. But you get it in more complicated cases. Also, remember, even though these cases look very simple, when you run Partition Backtrack, even if your group is horrible, once you've fixed a bunch of points, you're eventually going to get to a point where your group's just a mass direct product of loads of stupid little C7s and D8s and nonsense. And you still also have to chew through all of these, and there's loads of them. So writing a special case that detects you have a cyclic group is usually not worth the effort. You just get naughty to do it. So this is kind of where things stood. The fundamental thing that started to block us was the fact that all the refiners, our knowledge is represented by this function from omega to colors. And if you have two groups, the only way they can communicate is via this function. We've designed our framework so the groups cannot communicate with each other directly. All communication goes through the function. And once again, for boring technical reasons, you do not want the groups talking to each other directly. There are various invariants which have to be preserved, which there's a paper I'm going to talk about in a minute. You can read our paper, which will hopefully make Leon's work easier to understand. So you only want communication to occur through your function. If you are intersecting transitive groups, you can prove you can never do anything. It's not a matter of not being clever enough. If I start with the whole partition and I say to a transitive group, refine this function, it can't do anything. I say to the other group, refine this function. So it's not a matter of the people who write refiners aren't clever enough, it's just impossible. Now you fix a point and then you go down and maybe everything gets sorted out. But if your intersection is trivial and your groups are, say, on 250,000 points, which is a reasonable amount to ask, you have to say, well, I'll fix 1. Yeah, it's trivial. I'll fix 2. It's trivial. You've still got 250,000 branches, which takes a reasonable amount of time, gets quite annoying. So an improvement which I made with Wilf and Rebecca Waldecker and Marcus Pfeiffer was we extended this store of information to just contain more stuff. So now refiners don't just have to return a partition, they can say the answer has this block structure. It preserves this directed graph, it preserves this hypergraph, and then it's the internal solver's job to deal with this. And this actually makes making refiners even simpler, because it used to be refiners internally would build graphs, and then each refiner would have to worry about doing its refinement of the function. Now everyone just goes, no, here's a giant pile of stuff, like graphs, block structures, whatever I've got lying around. Then that bit of code in the middle obviously gets super complicated, because it has to deal with all these structures. But it can be done, and we did it. So there's a paper called Permutation Group Algorithms Based on Directed Graphs. So I will say, this paper, so we have an implementation in this paper, it demonstrates that the size of searches are massively reduced. This code is not fast yet. Our next plan is to make it go fast. We see no reason it should not go fast, because all we've really done is push the people doing the refining from inside the refiners into the central system in some sense. Just to give you a feeling for why this might be a useful thing to do, so if I had this group and I also had another cyclic group, so these two are both transitive, once I have both graphs at the same time, obviously this vertex here has the red and blue arrows coming out of it go to different places. So this vertex is this vertex and this vertex are the only vertices where the red and blue arrows coming out of them go to different places. So these two we can color differently from all these ones, and as soon as we've done that, the fact we have the red cycle fixes everything. This is very similar to the reasoning which Brendan Mackay already did. You have to slightly extend it to cope with the fact that now your graphs have multiple edges and they're different colors, but it's not a fundamentally difficult concept. And you can just pile all the things in together. So as I say, so what we are working on now is piling all these things together. I'm just going to tell one small anecdote, just in case anyone is tempted to get involved in this. Well, no, just to sort of say. So when I first spoke about this with Rebecca, she said, so we were talking about the bit where we're doing the group intersection, and she said, oh, and of course, if you have two groups G and H and you intersect them and their size is a coprime, then of course the intersection is trivial. And I said, that's true. And I said, but we went and we put it in, and it made a whole bunch of things go faster. So there really is low-hanging fruit. I mean, we've now done that one, so I'm afraid. But there is low-hanging fruit in this area. In particular, any other, we've kind of come to a natural ending. So like orbits, block structures, orbital graphs, these are obvious structures to build. They're not too big, so they're cheap to build. They're not too big, and they contain a lot of information about the group. So there's probably other structures we could build as well. Also, we could probably just start shock horror doing some actual proper group theory instead of just hitting orbits and orbital graphs until we produce the answers. But yeah, so that was a brief. So just to say, so if you do want to read this stuff, my personal advice, and I may well be biased, read Practical Graph Isomorphism 2, read this paper. If you can read German, you can read Heiko's thesis, although do be warned, no one seems to have an electronic copy with the pictures in it. And then if you're feeling really brave, you can read Leon's paper, but to be honest, I just wouldn't. But we should all acknowledge that he did the work. And I want to re-emphasize, it's all everyone's been doing for group permutation, group intersection for 20 years. So it was amazing, and it's what we all use. Anyway, I'll stop now. Thank you very much.
Questions? Alexander. When you calculate normalizers of group which are not simple, it might be, it seems tempting to calculate characteristic subgroups which you can get reasonably cheaply and first calculate the normalizer of these. And in some cases it is faster, in some cases it just is twice, and then a calculation which overall is slower. Have you tried anything like this, or is there anything one can say to that strategy?
There's nothing. So I'm going to be honest, because I have up until now been tending to look at all the bits that were not normalizer, because as you say, there's a whole bunch of other things outside of this box one should be doing. So I've been sort of trying to understand this box better. Normalizer is the next thing I read. Well, so Muncie's looking at some things. The bit where Muncie said in her talk, some bit, she said, this bit is very hard. What she also meant was we basically plug it into this type of machinery. So we are looking at ways of plugging more stuff into it, but for that type of thing, once again, being inspired by AI, what we'd really want to do is just in parallel set off 3 or 4 different strategies and let them all keep bringing information back as they finish. This is typically done in AI systems. They just do everything at the same time and see who finishes first.
So will your software now include a dependency on Naughty?
No, because I've written my own Naughty, because Naughty doesn't do edge-colored graphs. But it's very. Also, I kind of need. You can imagine almost like in this case, I start with this graph, and then I acquire this extra blue information. So I need, as the search progresses, I need the graph to be able to change. And Naughty, if you try doing that, just gets very, very upset with you. But my code will basically be almost exactly the same as Naughty, just my re-implementation of it to support this. And it's not theoretically deep, it's just programming.
And this will be part of Ferret?
This will be a fresh implementation. There were design decisions made in Ferret which were a mistake. There are technical. So I didn't talk about this at all. There is a whole other thing. So also in Leon's paper he writes, one of the things he writes is, I'm going to write a sequel to this. So this paper is called number 1. I'm going to write a sequel to this paper. And that sequel will tell you how to do canonical images, which he never wrote. Oh, well, for all I know, who knows, sometimes review takes a very long time. I'm now convinced I know, okay, I think I know how he meant to do it. Certainly I know how to do it, but I made design decisions in Ferret, which means it's not possible. So I'm going to make another one, and that one will do canonical images. Yeah.
Further question?
Well, can I just ask, what is the smallest integer n for which you can find subgroups G and H of sim n where it's difficult to calculate the intersection? I mean, what sort of size are we talking about?
So if I slightly adjust your question and say cosets,
Yes.
then about 14. So in particular, this is a good example. If you intersect the alternating group with its coset, all of this stuff breaks. Like, what are the orbits? It's everything moves. What are the orbital graphs? Nothing. If you give that now, we could in GAP special case that specific case, and we haven't. But in both GAP and Magna, I did check. Yes, if you ask that, now you shouldn't be asking them to intersect the alternating group and its coset. But if you do, you just hit the exponential case because none of this machinery does anything. And it's hard to imagine anything one would do except special case the alternating group, which is not, of course, an unreasonable thing to do. It's such a weird group. It's highly transitive. But that's how you hit the worst case.
Was that n equals 14 or 40?
14, 1, 4. Because it's 14 factorial, which is a decent number. Well, over 2. So
But for straight intersection.
for straight intersection, I think round about sort of 40 or 50. There's probably cleverer ways of getting smaller ones. What you basically need to do is get that kind of situation and just hide it.
Right. So algorithms which would be only useful up to the degree of about 1,000 would still be useful.
Yes. Although, of course, you can, and people do use this on groups with like 100,000, 500,000 points.
If you're lucky. Yeah.
If you're lucky. So, but it is a big gamble as to whether it works.
Yeah. Okay. Thank you.
Okay. I think we'll wrap up by thanking Chris for his talk.